like a time. Go. Okay. Hi, everybody. So we are going to finish up chapter 16 with the remaining slides, which is a little bit about talking about anions acting as bases, hydrolysis, and really thinking about different salts and when they're dissolved in water and whether or not we can assume if they would be acidic or if they would be more basic. So if we have a reaction with an anion with water, anions are going to give us a base, so we're going to get more of a basic solution. So dissolved salts, so first before we even talk about anions, let's just say that a dissolved salt, which means like NaCl, I could have rubidium sulfide, anything like that. If I have any type of dissolved salt, then when the salt dissolves in water, it could turn the pH acidic, or it could turn the pH to where it would be more basic. So there's some general rules that we have to help us determine if the salt is going to make more of an acidic solution or more of a basic solution. So anions, or actually even before we go there, just kidding. All salts we think of as being, or nearly all salts, are very strong electrolytes. So we can assume that any salt that dissolves in water will completely dissociate, okay? Let's just go ahead and think that way. So consequently, the acid and base properties of salt solutions are going to be due to their anions and their cations. So many anions react with water, and those anions that react with water usually produce either hydrogen ion or they're going to produce hydroxide ion. So depending on what they produce, we can then think about the pH of the solution as being acidic or basic. So any salt that will produce hydroxide or that could produce hydrogen ion, we call that hydrolysis. So any reaction, reaction that produces H plus and or OH minus is called a hydrolysis reaction. RXN just being reaction. Okay, so whether or not an anion reacts with water to produce hydroxide is going to depend on the strength of the anion's conjugate acid. So let's say that again. Whether or not an anion reacts with water. So if this, depending on whether this will react with water to produce hydroxide, to produce this, that's going to depend on the strength of the anion's conjugate acid. So it's going to depend on the strength of the conjugate acid, which is, in this case, HX. To identify the acid and to judge its strength, we know that we just add hydrogen to the anion's formula. If the acid is one of the 7 strong acids, and this is just a very general case, we don't have an element that's called, we don't have an element that's just X minus as an anion. So if the acid is one of the 7 strong acids, so if the acid, the conjugate acid here that we form, if that's one of the 7 strong acids, then we think about the pH of the solution not being affected. Because remember, when we look at that chart from the beginning of this chapter, so let's say that this was Cl minus, and I know if I add the conjugate acid to that would be HCl. Well, that's a strong acid. And if we looked at that chart in the first slides of the PowerPoint, I looked at HCl and I saw that that was a strong acid, and if I looked over at the base side, the base was like negligible basicity, meaning that this isn't going to really affect pH at all. So because it's a strong acid, or any strong acid, will not affect the pH. So any strong acid, so if I'm finding my conjugate acid, and if that conjugate acid is a strong acid, pH is not affected. Okay, if it is not one of the 7 strong acids, then we consider it to be a weak acid, of course. So we will get some hydroxide that we're going to produce. And if we're producing hydroxide, then that means we're going to have some base that's produced, or the pH is going to be more basic. So if this is, instead of Cl minus and then HCl, let's just say that this is the acetate ion. So now we have C2H3O2. So that means the conjugate acid here is going to be acetic acid, C2H3O2. And I know that's a weak acid. And in a weak acid, if I look on my, if I'm thinking about my chart again from the previous slides, a weak acid is going to also have a fairly weak base as well. But at least I know that I'm going to also be generating more of this. So my OH minus concentration is going to increase if I have a weak acid as my conjugate acid. So that's going to increase my pH of my solution, which is going to make it more basic. Let's go back. Okay, let's think about cations. Anions are going to ultimately, like we said, make the pH more basic, as long as it's a weak acid. Strong acid isn't going to have really any effect on pH. So we can also think about reactions of cations with water. Cations are going to make more acidic protons, or cations that have more acidic protons, they're going to lower the pH of the solution. So cations are going to cause more acidic solutions. And remember, if we lower the pH because if the pH is lower than 7, then that means it's acidic. But if the pH is higher than 7, that means that it's basic. So if we lower the pH, that means we're going to have an acidic solution. So most metal cations that are in water, that are hydrated just meaning they're dissolved in water in a solution, lower the pH. Okay, so another effect of just cations, but just so that way we add this here too, and I think we may see this in the next slide. So most cations, again, they have acidic protons. Or maybe I don't have an acidic proton. Maybe I don't have an H+ with something that I'm reacting into water. I'm trying to dissolve in water. Maybe I have something like Fe2+ or Al3+. I want us to add that small cations will also, and let's say small, I want to change that even more, small highly charged cations can also lower the pH of a solution, and that's just something that we have seen experimentally. So Fe2+, Fe3+, those are small cations. Aluminum 3+, that's another small cation that has more positive charge. So those can also lower the pH. Okay, so why does that happen? Why do cations lower the pH of a solution? So ultimately there's an attraction between non-bonding electrons on the oxygen of a water molecule and the metal. So I have my metal cation and I have my lone pairs on those non-bonding electrons for water. Because remember, we have water, I have H, and then I have those 2 lone pair on the oxygen. But then I have this, let's say we just have aluminum 3+. But then I have an aluminum, and aluminum may want to have or share some of that, there's an attraction between this aluminum and that lone pair with that oxygen. So ultimately what's happening, we have a shift in the electron density then of water. And so because of that, it's going to make one of these OH bonds more polar than the other one, so then the water then is going to become more acidic. Okay, so also with cations, okay, we already said that. The greater the charge and the smaller the size, it makes the cation act like it will be more acidic. So the solution that we have, the pH would be more acidic. So we've already said that. And I can see that here with Ka values. So let's just kind of talk about some rules when we're thinking about effective cations and anions. Number 1 says, an anion that is the conjugate base of a strong acid will not affect the pH. Anion that is the conjugate base of a strong acid will not affect the pH. Okay, so if the salt contains an anion that does not react with water and a cation that does not react with water, then I assume then that the pH is just going to be neutral. So this is going to happen, like we just set up here, when the conjugate base of when we have a conjugate base of a strong acid. So we just saw before, let's say we have Cl minus plus water. And that produces HCl plus OH minus. So when it says the conjugate base of a strong acid is not going to affect the pH, well, this Cl minus is the conjugate base of HCl, if I'm looking at the reverse reaction here. So Cl minus, we know that the strong acid HCl, if I go back and think about that chart from the beginning, I know that Cl minus has like negligible basicity. So because of that, it's not going to affect the pH. So this is going to be true for salts like NaCl or BaNO3. BaNO3 too, just kidding. Or I could have rubidium perchlorate. The reason that I'm showing you these, so today in class, remember that we showed the net ionic reaction when we're talking about acids and bases, and we have specifically a salt that we're now dissolving in water. So remember we said that sodium can act like a spectator ion. So I can think about Cl minus reacting with water, and then Cl minus, we know, is a conjugate base of a strong acid HCl, and we just said that that's not going to affect the pH very strongly. Same thing here, BaNO3 too. NO3 minus is the conjugate base of a very strong acid, HNO3. So because HNO3 is a strong acid and NO3 minus is the base, it has negligible basicity, so again, it's not going to affect the pH. Same thing here, HClO4 is a strong acid, perchloric acid, and RB really isn't doing anything. Those are just kind of spectators. So those would be some examples of salts that would not affect pH at all if we dissolved them in water. Okay, number 2, let's look at number 2. Number 2, it says an anion that is the conjugate base of a weak acid will increase the pH. So conjugate base of a weak acid will increase pH, meaning that it's going to make it more basic. So this would be basic. Okay, so let's look at an example of that. That would be like if I have an anion, any conjugate base of a weak acid. So I know a weak acid could be acetic acid, so the conjugate base of that would be C2H3O2 minus. So if I paired that with something, like if I just paired that with sodium, so if I had sodium acetate, that could be something that if I added to a solution, it would increase the pH by making it more basic. Another weak acid could be hydrofluoric acid. So if I had HF, then the conjugate base of HF would be F minus. So maybe I had just sodium fluoride, and I added sodium fluoride then to water. That's going to increase the pH because I know that the conjugate base of the weak acid should increase pH. So these are just some other examples. If I have an anion that's the conjugate base of a weak acid, then those are going to increase the pH, meaning that they're going to be more basic solutions. Just like what we talked about with cations, let's go to number 3. A cation that's the conjugate acid of a weak base is going to decrease the pH. So a cation that is the conjugate acid of a weak base will decrease the pH. So an example of that one. So a weak base, let's think of a weak base here. Ammonia. Ammonia is a weak base, NH3, and it's not, and I know that because it's not one of those 8 strong acids that we had to know. So I know that ammonia is a weak base, and I know that the conjugate acid of NH3 is NH4+. So the conjugate acid, this is a cation, and that's my conjugate acid, and that's a cation of a weak base. So because this is present, I know it's going to decrease the pH, thus making it the solution more acidic. Okay. Let's keep going, guys. Cations. We'll just kind of go through these quickly. Cations of the strong Arrhenius bases will not affect pH. So if I think about those strong bases, NaOH, I think about KOH, I think about BaOH2. So they're saying that these cations, Na+, K+, Ba2+, aren't going to affect the pH at all. It says other metal ions will cause a decrease in pH. So those would be like those small, greatly charged cations. So like Fe3+, or Fe2+, or aluminum 3+. Any of those can have a small decrease in pH, making it more acidic. So this would cause a solution to be more acidic. And let's say when a solution contains both a weak acid and a weak base, then ultimately the effect on pH is just going to depend on one of these types of values. Okay, so my goodness, there's all these rules. What on earth do they mean? Well, let's kind of go through some examples and work our way through this. So let's start off with the first one, which is BaCH3COO2. Well, this is just C2H3O2, so I have barium acetate here. So my goal is to figure out, these are all aqueous solutions of each of these salts, and I want to determine, once I add this to water, once this is now dissolved in the water, does this addition of this salt make the solution acidic? Does it make the solution basic? Or does it make the solution neutral? So I have barium acetate. I know that acetate is my anion. So C2H3O2-, that's my anion. And I know that the conjugate acid of this anion is a weak acid. It's acetic acid. So we said in one of our rules before that if it is a weak acid, so the anion that is the conjugate base of a weak acid will increase the pH, thus making it, what did we say, more basic, right? So that's rule number 2. So let's just add over here, that was rule number 2 that we had. Anion that is the conjugate base of a weak acid will increase the pH. We just said that that makes it more basic. So I know right now that according to acetate, so far my pH is going to be basic. So I'm going to say that it's higher. So right now it's basic. And Ba. So we said that on the last rule, cations of the strong Arrhenius bases will not affect the pH. Well, I have barium hydroxide, and barium is a cation of a strong base. So barium, if I think about Ba, will have negligible effect on the pH. So that means really the only thing that's in play here that I want to think about is acetate. So that means that ultimately this solution, barium acetate, is going to increase the pH, making it basic. Okay, so now let's think about NH4Cl. So I have ammonium chloride. So again, this is basic. Okay, well, let's just break apart each one. Let's look at each ion specifically. Well, Cl would be Cl minus, and I know...
I have a couple of afternoon announcements.
So Cl minus is, if I take the conjugate acid for this base, that would give me HCl. HCl is a strong acid. So because that's a strong acid, that means that this base has negligible basicity, meaning that it's not going to affect pH at all. So Cl is not going to do anything for us in terms of pH. NH4, however, let's look at it. NH4 plus, it is a cation of a weak base, which was NH3.
Your pictures are at 2:30, and your
And according to one of our rules, which was number 3, a cation that is the conjugate acid, NH4 plus is a conjugate acid of a weak base, NH3, is going to do what to pH? It's going to decrease pH. So NH4 is based on rule number 3, that it is going to decrease pH, so this is going to be acidic.
Garrett Dexter, Eric Albino.
Okay, I would like you guys to try these 3 for me, and we'll go through them together in class tomorrow. That'll be the first thing that we do whenever we come into class. So that's going to finish this, but we're going to have one more very small video, so just be prepared.
Logan Leahy, Chad Lance, Josh Baker.